Hello, my name is Sergey Kucherenko. I am from Imperial College London, and my talk is about application of machine learning and global sensitivity analysis for identification and visualization of design space. This work was done in collaboration with Alexei Klimenko and Nilay Shah. Pharmaceutical products should be approved by a regulatory body to be manufactured on the condition that there is enough evidence to demonstrate the safety and efficacy of the drug product, and that the manufacturing process has controls to assure the quality of it. These controls represent a set of admissible operating conditions that provide an assurance of quality, accounting for variations in the materials and manufacturing processes. They are commonly referred as the design space. Identification of probabilistic design space is a demanding task, and for a typical practical problem, the traditional approach requires very costly computations. The outline of my talk is this. I will talk about definition of design space, about global sensitivity analysis and machine learning as tools to improve efficiency of computations. I will consider a case study, which is a batch reactor. I will present the results of application of machine learning and global sensitivity analysis for identification of design space. Finally, we'll talk about visualization of multidimensional design space shapes. And I'll leave you with some information about Sobol GSA, which is global sensitivity analysis and metamodeling software that was used to get these results. Design space is defined as the multidimensional combination and interaction of input variables, such as material attributes and process parameters that have been demonstrated to provide assurance of quality. Concept of design space is widely used in pharmaceutical and chemical industry. It is not possible to operate a chemical plant at a precise point due to uncertainty. Therefore, we need to find the range of operating parameters within which the process can be operated successfully. Consider a model y as a function of vector x and a vector theta, and the constraints KPIs function g, function of x and theta, where x is a vector of controlled variables defined in the box domain Hn, and theta is a random vector of uncertain parameters with a given PDF. Then define probability map such that probability as a function of vector x is an expectation with respect to theta of a condition that an indicator function I with argument that vector of constraints g is larger or equal than a critical threshold g star. Once Px is defined, we can identify design space as a set of points x such that probability of x is larger than a critical or acceptable value of probability. Probability Px can be presented in a convenient for simulation form as an integral given here. Once probability map is identified, we can use a Monte Carlo estimator for estimation of this integral. A Monte Carlo estimator works as this. We generate n s points in the space of control parameters x. For each n s point, we generate n theta uncertain parameters, and we compute probability by counting the number of simulations and feasible for which constraints are met for each point xk. And then the ratio of all accepted or feasible points to the total number of points would give us probability in the specified for each point pk. The total cost of this approach will be ns multiplied by n theta. As we show later, this total cost is extremely large for even small problems. Therefore, we need to apply some other tools to reduce this number. Here, I'll present briefly ANOVA decomposition and Sobel sensitivity indices, which are the basis of global sensitivity analysis. We consider a model fx, where x is a vector in a hypercube Hn, and ANOVA decomposition is such that function fx can be represented in this form, and this decomposition is unique if conditions such that an integral of each of these terms in ANOVA with respect to a subset of parameters xip, if this integral is equal to 0, then all terms in this decomposition are orthogonal, and because of orthogonality we can decompose total variance into partial variances presented here, and then if we normalize this expression by total variance v, we'll get what is known as Sobel indices. Global sensitivity analysis is a widely used tool for identification of key parameters whose uncertainty most affects model output. On this slide, I present a second tool that we use in this work, and this is a machine learning method known as random sampling high-dimensional model representation. It is based on the ANOVA decomposition such that we cut all interaction terms in the ANOVA decomposition above a certain threshold. Here we assume that there are only main effects given by fi xi and interaction terms fi fij, second order terms. Once we assume this form for ANOVA decomposition, each of these terms in ANOVA are decomposed using orthogonal polynomial expansions, as given here for fi xi and fij, where phi's are orthogonal polynomials, and the coefficients of these decompositions can be obtained either by using projection method, given here in the form of integrals which are evaluated by using Monte Carlo or quasi-Monte Carlo methods, or these coefficients can be estimated by the regression method. The details of this method is given in this publication. On this slide, we consider a case study which is a simple batch reactor in which the following reaction takes place. The processes in this reactor are described by the system of ODEs, with parameters theta, which is collection of activation energy and reactor rates E and K correspondingly. And these parameters are estimated from experimental data. And we are interested in two KPIs, namely profit and purity, which depend on the concentration of the final product and byproduct. And so the parameters are assumed to be given by normal distribution with estimated values of mean and sigma. In this case study, process parameters X would be operating temperature T and processing time tau. The task is to determine space of process parameters T and tau such that at least 80% of product B is in the final product. That would be the threshold for the first constraint, and the economic performance of at least $128 per minute. That would be the threshold G2 for the second constraint. As we remember, then the probability map would be defined by this integral with a product of two indicator functions. If we apply the brute force approach that we presented for identification of design space, to obtain good results, we would need the total number of sample points and model runs to the power 23, which is very large number, and it's not acceptable for this small problem. We develop a technique based on meta model as an acceptance rejection criterion. It works like this: we sample some number of points in the tau temperature domain. We build a meta model in this domain. Then we check if a probability defined by using a meta model belongs to the design space domain. If yes, then we select the point, and for all selected points we run the full model and compute probability map, actual probability map. When we do that, we have 200 times speed up. On these slides, we see some results for this problem with accepted points as red. The details are given in this publication. On the second step, we applied global sensitivity analysis, which revealed that only one parameter out of 4, namely K1 rate, is important. These results were used for complexity reduction, namely by fixing all other not important parameters to their nominal values, therefore reducing a dimensionality from 4D to 1D. With this reduced model, we identify design space, and results presented on this plot show that the design space shape is identical to the benchmark result, but obtained with much lower number of points in the process parameter space. And the application of both machine learning and global sensitivity analysis results in 8,000 times speed up. Finally, we'll talk about visualization of multidimensional design space shapes. Guidance for industry has the following recommendations. When multiple parameters are involved, the design space can be presented for two parameters at different values, that is high, middle, and low, within the range of the third parameter, the fourth parameter, and so on. Considering design space in a d-dimensional parameter space, a graphical presentation of DS via 2D plots would result in this number of plots. For example, in the case of only 6 parameters, this NP number will be 1215. We consider this problem of visualization as a class of models with constraints. We can apply global sensitivity analysis for constrained problems. And let's assume that this analysis would reveal that i's parameter is not important. It means that all 2D projections will be the same regardless of the value of xi. Hence, instead of 3 values, high, middle, and low, for this parameter only 1 is sufficient for the graphical representation, which would result in the reduction of NP to this number of plots. And in the case of S non-important parameters, this number will be reduced further. For illustration, we consider 2D visualization of the model given by the so-called Sobol G function given here. This function has parameters ai's, and depending on I, this function has different behavior. Now, design space in this case will be defined by the constraint that function fx should be larger or equal to 1. We consider 3 sets of parameters I, A, and in the first case, all 3 parameters are important, and we would need 9 2D projections. In the second case, only first 2 parameters are important, and we need only 7 2D projections. In the third case, only the first parameter is important, and we need only 2 2D projections. And it clearly can be seen from these plots that indeed, depending on values of parameter a's, 2D shapes can be either identical in some projections or different. To obtain these results, we used Sobol GSA tool, which is a GUI-driven tool for global sensitivity analysis, uncertainty quantification, and machine learning, which can be downloaded using this link. Thank you for your attention.